In this video, we'll be looking at the simple pendulum. The simple pendulum is ideal and it executes simple harmonic motion. If we look at a diagram of the simple pendulum, it consists of a point mass connected to a string attached to a frictionless support. Because the simple pendulum is ideal, the mass of the string and the friction forces are neglected and a point mass is used. In the first diagram, the pendulum is in vertical equilibrium. If we draw in the forces, the force of gravity acting on this mass is mg. Because the system is in equilibrium, there is an opposing force that balances the mg, which is the tension in the string. We're going to call this Ft. In the next diagram, the mass, or the pendulum bob, is displaced from the vertical equilibrium position by an angle theta. The vertical equilibrium position was here, and the displacement to the new position is s. And the displacement is related to the angular displacement by the formula S is equal to L times theta, where L is the length of the string here. The angular displacement is positive to the right and negative to the left. If we draw in the forces of the simple pendulum, there's a force of gravity acting on the mass, mg, and the tension force, Ft. To analyze the motion of the pendulum, we have to resolve mg into two components. So we have mg cos theta and mg sin theta. Along the length of the string, right here, this is called the radial axis. Perpendicular to the radial axis and along the motion of the pendulum, or the circular motion, right here, this is the tangential axis. As you can see, the component along the radial axis is mg cos theta. And because the motion of the pendulum is not along the radial axis, we can say that this component, mg cos theta, is equal to this component, which is the force from the tension. The component along the tangential axis is mg sin theta. And this provides the restoring force that pulls the pendulum bob back to the equilibrium position, right here. And if we use Newton's second law of motion, F net is equal to ma, but for the tangential component, we get F net of t for tangential is equal to negative mg sin theta. And we use sine theta and cos theta because this angle here is theta. You can see that there's a negative sign here, and the negative sign is important because when we pull the pendulum to the left or to the right, the mg sin theta, which is the restoring force, will want to push it or pull it back to the equilibrium point. That's why mg sin theta is negative. It will always pull the pendulum in the opposite direction back to your equilibrium point here. So F net tangential is equal to mg sin theta negative, which is equal to your negative m acceleration tangential. The tangential component of acceleration is equal to negative g sine of theta. And if you recall from the previous slide, theta is equal to s over L. So our final formula is a sub t is equal to negative g sine s over L. So the equation that we obtained was the tangential component of acceleration is equal to negative g sine of s, which is the displacement, over L, which is length of the string that connects to the pendulum bob. The equation for acceleration of a simple harmonic oscillator is this. Where this is omega, so the acceleration of simple harmonic oscillation is omega squared x of t, where x is your displacement and the entire thing is negative. So these two equations, they aren't exactly the same, but if we use small angle approximation, then they are approximately equal. So if you look, this is the degree of theta in our case, and this is the radian value, and this is the sine value. As you can see, these values are really close to each other. So if we use small angle approximation, then we can say, instead of negative g sine s over L, we can say a of t is equal to negative g s over L. So if we recall from our previous slide, we got negative g sine of s over L is equal to negative g s over L using small angle approximation. Now if we compare this to the simple harmonic equation that we saw earlier, which is negative omega squared x is equal to negative g s over L, and we use algebra to find what omega is, we get this. Now if you recall, s and x, they're both displacement. Which means in our equation we can cancel these out. We're left with omega is equal to the root of g over L, where L is the length of the string and g is force of gravity. And omega here, this is your angular displacement. And as the textbook says, for small angular displacements, the acceleration of the mass is proportional to the displacement and opposite in sign. Therefore, the motion of the pendulum is simple harmonic motion. So next, we're going to look at the period. So if we have the period is equal to 2 pi over omega, and from our previous slide, we found that omega is equal to the square root of g over L, then we can just combine these two equations and we would get the period is equal to 2 pi times the square root of L over g. And this is the period and the frequency of the oscillation of a pendulum. So looking at this equation, we can see that the period is dependent on the length of the pendulum, L, and the acceleration due to gravity, g. This means that the period of a pendulum will vary as the value of g across Earth's surface varies. So it's possible to measure the variation in the value of g across Earth's surface while measuring the time with a stopwatch. So the major learning goals that we went through in this video is understanding the simple pendulum and understanding how the pendulum period, t, is related to the physical values g and L. So now let's try one of the problems from the textbook. In the table, the lengths and masses of 6 pendulums are listed in the table. To rank the pendulums in order of the periods, let's look at the formula we found in the previous slide. So the formula that we found was t is equal to 2 pi square root of L over g. Looking at this formula, we know that the period is dependent on the length and not the mass of the pendulum. This means that the largest period would have the largest length. So if you have a mass on a short string, like so, and you wanted to oscillate it back and forth, compared to a mass on a longer string, and you're going to oscillate it back and forth, this one would oscillate much faster than this one. So if we're looking back at the question, the one with the smallest period is the one with the smallest length, and which would be A, because 0.8 meters is the smallest. And then it's 0.9, and then it's 1.1, 1.7, 2.1, and 3.2. So the answer would be A, D, B, C, E, F, in order of increasing period. Oops, spelled that wrong. And that concludes the video. Thank you for watching.